All right, welcome back, ladies and gentlemen. Today we're going to be doing a lot of review. It's good for you to hear things more than once. Friction is a force that resists motion, and there are two kinds. Where's my mouse? We've got static friction, which resists the start of motion. So static is not moving.
So you're pushing on something, it's not moving. That's static friction that's resisting you. And static comes from the same word as stationary.
Ooh, nice connection there.
Not moving.
And then we have, oh, no, wrong. What was the maximum static friction before your block moved? Well, just the block, it was negative 1.4 newtons. Kinetic or dynamic friction is the sliding friction. So when something is sliding, it's the friction that an object experiences as it's moving.
When we were pulling on the block with a spring, it built up to a maximum amount of force. Then when it started moving, it was less force.
So this resists motion while in motion.
Yep.
What happened to the friction when you added the 1 kilogram mass?
That was going from 1 to 2, right? That doubled the friction.
It increased it. In this case, it doubled it. What did the paper do to the force of friction?
So that's going from 2 to 3. Whoa, that's goodness.
Chopped
28
it.
divided by 6. That's like what, a fifth?
Well, yeah, it reduced it by a lot. We'll say that. Okay, a lot. And so how much friction depends on two types of things. What kind of surfaces are in contact, paper versus the wooden table,
yep.
And how tightly the two surfaces are squeezed together by the normal force.
Yep.
And by adding that mass on there, we increase the normal force. More normal force equals more friction. There is a relationship here. More normal force, more friction.
Yep.
The properties of these surfaces determine the coefficient of friction, mu, which is determined thus. Here is our equation. Force of friction, normal force, gives us mu.
You guys calculated this yesterday, I do believe.
You calculated your 3 trials.
And what is mu?
The sound the kitty makes. No.
Click, click, click. There it is. It is. It's the sound the kitty makes.
Oh, it's so cute, little kitty cat.
Cute little kitty. Look how sharp those teeth are, you know. Razor sharp teeth.
Oh, looks like my cat.
God's perfect killer.
Okay, and so you guys determined the coefficient of friction for all of your trials. And we went over that in class, hopefully before this video.
Yeah.
Okay, in a horizontal system, the normal force is equal in magnitude and opposite in direction than the force of gravity. Normal force, force of gravity.
So if the system is horizontal and you know the force of gravity down, you also know the normal force up. That's an important thing.
Very important. And so before we had mu equal the force of friction divided by the normal force, and we just moved that over here.
Yep.
And now we've got the force of friction equals mu times the normal force.
So if you know the normal force and the coefficient of friction, you can calculate what the force of friction is going to be.
Okay, let's do some practice.
A ½ kilogram block slides to a stop across a table. Ooh, ooh, that's going to look like this. Whoop. Do that again. All right.
Okay, so we've got our 0.5 kilogram block. Okay, and we said the mass was 0.5 kilograms. Let's put that up here. So mass was 0.5 kilograms.
If we know the mass, what can we calculate?
We can calculate the force of gravity then. Force of gravity is mass times gravity, which equals my 0.5 times negative 9.8 kilograms meters per second squared. So let's see, 0.5 times negative 9.8, and I get negative 4.9. Negative 4.9 newtons.
So if we know the weight, boys and girls, what else do we know?
Well, we talked about, we also know the normal force. It's just going to be positive.
Yep.
4.9 newtons. Okay. It slides across the table
To a
to
stop.
a stop. Okay,
That's-
so the fact that it was moving, there was some friction there, and our coefficient of kinetic friction is 0.29. No units for this. Draw a free body diagram showing all the forces. Okay, well we also had a force of friction, right?
And we can calculate that how much that is if we have the normal force and the coefficient of friction.
Yes. So let's go ahead and use our equation. We know the force of friction equals mu times the normal force.
Yep.
And we know our force of friction is 0.29
Coefficient of
times.
friction.
Oh, sorry. What did I say?
The force, but it's okay.
Oh, coefficient of friction times 4.9 newtons. And that's going to get me 0.29 times 4.9, and I get 1.42.
1.42, so that's the force of friction. You can add that to your free body diagram. Now, if it's sliding across a table, you've tossed it across a table, it's sliding to a stop, is there any force in the other direction, boys and girls? Is there?
Nothing's
No.
pulling it.
No!
Attention all students, if you still want breakfast being served for the next 10 minutes down at the cafeteria windows.
Go get it, go get it. Okay, so, yeah, there's nothing in this direction.
So I think we're done.
We're done, we're good. Draw up your diagram showing all the forces.
No, we're not.
Oh, and acceleration.
How can we know the acceleration?
Okay, well, the net force, well, let's go ahead and cross them out. These and these cancel, right?
Yeah, they do.
And does anything cancel with this one?
No, that's the net force is equal to the force of friction.
So if the net force is this way, the acceleration must be in the same way.
Excellent.
That just means it's a negative acceleration, which means it's slowing down.
That's right.
Boom. Okay.
So, but we haven't calculated the acceleration.
Oh, we have to calculate it. Showing all force and acceleration, you're right. What was that equation?
I think it's Newton's second law.
Okay, so we want to figure out our net force.
The mass is half a kilogram.
0.5 kilograms times my acceleration.
No.
Oh wait, that's what we're trying to find.
So how do we solve this for
So
the net force
our net force
is 1.42.
1.42. And that's because these two cancel out.
Yep.
This one's what's left. This is our net force.
How do we solve for A?
Let's just go ahead and divide by this. I was like, wait, are we trying to find the net force and the acceleration? I forgot.
That's going to be 0.71, I'll bet.
Let's see if he's right.
The human calculator.
1.42 divided by 0.5. Oh. 0.5.
It's divided
2.84.
The human calculator.
Wrong
fails
again. So acceleration equals 2.84.
Notice that Ms. Moore went to the calculator wisely
Ain't no
rather
shame
than
in the
listening to
game.
the old man.
Okay, so that means that our acceleration this way is 2.84 meters per second, but it's negative. Oh, that's because of my force of friction, my net force is negative up
That's
here.
right.
I just forgot to put it there. Boom.
Boom, boom.
You notice how I caught that mistake? You know, does your answer make sense?
That's a very important thing to ask.
Looks a little confusing there. Okay. All right.
And I think we're done with this.
No, we have a couple more.
Oh,
Right.
no, I mean we're done with that.
Oh, yeah. Not done with this. Okay, so this entire time you guys have been hearing us say, well, actually, let me start up here. So if you have constant velocity, what's constant velocity?
Means it's not changing.
So our velocity is not changing, which means you're either not moving, you're at 0, or you're moving at a constant speed of 4 meters per second.
Sure.
Okay? And so if you have constant velocity, you are not speeding up or slowing down, you are not accelerating.
That acceleration is 0.
And if acceleration is 0, that means your net forces are all canceling out. So what's really important is that if you have one of these, you have all of these.
Yep.
So if our net force is 0, that means it's not accelerating. That means that all of our forces have to be equal. Now over here, do we have a net force of 0?
Nope.
No, which means we've got acceleration.
There is an acceleration.
So if one of these is true, all of them are true. When velocity is constant, acceleration equals 0. So the net force equals 0, meaning vertical and horizontal forces cancel out. Vertical and horizontal forces cancel out. Okay. Let's do some practice.
block weighs 10 newtons. You pull on it with 4 newtons, but it doesn't move.
I like the other one better. This one. This is the best one.
It's nasty, but it works.
It does the job. Okay. Okay, so a block weighs 10 newtons. We'll go just draw that in here.
What direction is weighs 10 newtons?
Weight is the force of gravity.
That'd be down. That'd be down. We down with that.
Weight is the force of gravity. Which was 10 newtons?
Yep. You pull on it with 4 newtons. Let's make that to the rate.
So where's my purple? The force of the pole. But it doesn't move.
What's the acceleration?
Okay, well first of all, let's finish drawing in our diagram.
Well, hang on. No, let's just go through this because we'll get to that.
Oh, okay. What is its acceleration?
Well, it's not moving.
It's not moving. It doesn't move.
Acceleration is 0.
Okay. Well then, what is its net force? Well, if the acceleration is 0, the net force by the dynamic trinity rules is also...
Yeah, also out of Newton's second law. Force is mass times acceleration. The acceleration is 0, the force is 0.
Mm-hmm.
There you go.
Okay.
Okay, so now.
So now, what is the normal force? So if acceleration is 0, net force is 0, that means that the vertical and horizontal forces all have to be the same and equal each other to cancel out.
That's right.
So that means I'm just going to go ahead and 10 newtons here. This is the force normal. And this one over here, again, it has to cancel out with this one. So my force of friction is going to be
-4 newtons.
-4 newtons. Yes.
Boom, 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 boom.
Easy.
Boys and girls, do you understand the rational
This is the key.
path we're following?
This right here is the key. You must know the dynamic trinity.
Okay.
A wooden block with a mass of 0.56 kilograms is pulled by a spring scale, just like how we did in lab.
Oh, yeah, that's right.
The maximum force just before it moves is 2.1 newtons.
That was a stunt.
I should probably lock my door. Okay, pausing for a second, guys. Mask up. Good morning, you guys. I'm shooting a lesson right now, so I'm so sorry. I have to keep this closed. Okay, hey guys, nice to see you.
Well done.
That was my kids from last year.
Just
Okay.
coming by to say hi.
I don't know what they're doing. Okay, a wooden block with a mass of 0.56 kilograms is pulled by a spring scale. The maximum force just before it moves is 2.1 newtons.
Draw a free body diagram.
Oh, I started to draw a free body diagram before I even knew it asked me to do one.
Woohoo!
Okay, so force of gravity is
Well, the mass is 0.56 kilograms.
-9.8 meters per second squared.
And the maximum force just before it moves is 2.1 newtons.
So that means, so the force of friction is the force that,
Now, do the pull first.
the force pull, okay. We'll go this way first. So just before it moves was 2.1 newtons?
2.1 newtons. You got to know that before you can know the force of gravity.
Okay. And then,
So
that
so
means
put the
that
friction in, yeah.
force of
Yeah.
friction is
Negative 2.1
negative
newtons.
2.1 newtons, okay.
So we've already got the weight. What's the normal force?
Wait, hold on, I gotta calculate the weight first.
Oh, sorry. We don't know the weight.
Speed racer! Okay, times a negative 9.8. Okay, negative 5.5. So what's nice is in AP Physics, we just use negative 10.
Don't tell them, don't tell them.
If you join AP Physics, that could be you. Okay, so this is the normal force, right?
Yeah.
The force up. And it's just going to be positive 5.5 newtons. Okay. Draw a diagram. What is the weight? What is the
Okay.
normal force?
What's the coefficient of static friction?
Okay, what was that equation?
The sound the kitty makes, mu.
Sound the siren makes. Equals the force of...
It's the force of friction over the normal force.
Thank you. Sometimes I forget these things. And our force of friction is negative 2.1 newtons divided by the normal force, which is 5.5 newtons. And the mu equals negative 2.1 divided by 5.5, and I get negative 3.38.
Boom.
That's it. Negative 0.3. No units if you don't include the negative. It's all right. Whatever you want. I think we've got one more. Yes, this is our last one. Okay. The same block starts moving. And requires 1.8 newtons of force to maintain a constant velocity. What is the coefficient of friction? What's the first thing we need to note here?
Well, you're changing some things.
What does constant velocity mean?
That means a no acceleration.
And that means that we have a net force of
0.
0, which means the old block starts and requires 1.8 of the same block starts moving and requires 1.8 newtons of force to maintain a constant velocity.
What do we have to change on our diagram?
So this is going to be 1.8?
Yes, it is.
Okay.
And since it's,
Well, and what were you going to say? Were you going to talk about this?
well, since it's moving, the force of friction is not going to be the same as before we were so rudely interrupted.
We got a phone call. So the force of friction is no longer 2.1 or whatever. Since the constant velocity, acceleration is 0, net force is 0. That means this and this have to cancel out.
Excellent. Well said.
This is 1.8.
So now, what's the same? What's different? We're going to find the coefficient of friction. Now it's kinetic friction.
Only difference. So mass is the same, or sorry, the normal force is the same.
Yeah.
But this up here is different. This number up here, and it needs to be negative 1.8.
1.8.
Newtons. Okay, let's do it. So negative 1.8 divided by 5.5, and I get negative 0.33.
And that makes sense. We have a smaller coefficient of friction because it's not static, it's now kinetic. Boom.
It's already moving.
Well done.
Okay, and yours is homework. I'm going to post some of these guys. Oh, actually, this is your homework. Sorry. Your homework is to read to comprehend page 131 right here. And not the whole thing. You guys are going to start 131. And we're in chapter 6. It says a model for friction forces. You're going to read from here to here.
Just one paragraph.
Just one little paragraph right there. And then do the example problems on page 131 and 132. So here's the beginning of the example problem. And boom.
And then another one. Oh, it actually goes to the
133.
next page.
That's right. Well, you guys, 1 to 1 and 130. Let's start at 132.
Sweet.
And one thing you want to notice is that these problems are different. In this first problem, it's balanced frictional forces, and over here it's unbalanced. Figure out what that means. Make sure you're paying attention to that. Okay?
All right.
Go ahead and begin.